So today we're going to start a discussion of one loop amplitudes. Okay. So to start with, we'll discuss the amplitude on the torus, and then we'll look at the cylinder, the Klein bottle, and the Mobius strip, and we'll try to get physics results from that. Okay. So let's start. Let's first look at the torus. So you remember that our general formula for so we're going to take 10 minutes just to understand torus amplitudes. Okay. So you remember that our general formula for scattering amplitudes, first in the bosonic string, was the integral over the moduli, product d tau I, and okay, so the integral over the moduli, and then for each factor of the for the modulus, there was this there was a factor of b with del tau g. All the moduli are going to come in complex conjugate pairs, so there will be a b. Well, this is overall moduli, holomorphic as well as anti-holomorphic. We'll be able to group them up. So this is the thing that, and then of course there was a certain number of fixed vertex operators, and then integrated vertex operators. Okay. So now let's remember that the number of moduli fields were the number of conformal killing vectors. Sorry, there's a number of the other way, the CKVs, wherever the zero modes of B. Were the number of moduli, and the C0 modes were the number of fixed vertex operators. Okay. Now let's look at so what we want to do is to know how many moduli there are, and how many fixed vertex operators there are. So how many B0 modes and how many C0 modes there are. Okay. Well, this is a very easy calculation, because in one particular choice of conformal frame, the torus is simply dz bar ds squared is equal to dz bar with the following identification. Z is to be identified with z plus 2 pi I, or 2 pi, yeah? And z is to be identified with z plus 2 pi tau. Okay, so this is sometimes drawn as follows. This is the complex plane. There's one line here which is of length 2 pi, and there's another line here which is of length 2 pi tau. Right? 2 pi, right. And tau gives you the angle. The complex number tau gives you the angle. So if tau is pure imaginary, then it's an identification up here. Tau has a real part, it goes that way, and so on. So this is the torus. So what makes the space very simple is that the metric is just flat. Okay. So it's very easy to compute the B0 modes and the C0 modes. Okay, because the C0 modes are simply exactly the vectors are simply del z bar c is equal to 0. So you might at first think, well, it's just absolutely any analytic vector. However, the vector field has to respect this periodicity. So consider the most general analytic vector, it's some Taylor series z to the power n. Clearly we won't respect the periodicity unless this thing is a constant. Okay. So the analytic and the anti-analytic C0 modes are just C is equal to, constant. The fact that this constant could be complex, okay, is the fact that there are two zero modes, which we can think of as vector and complex conjugate. That will be the C0 mode and the C bar 0 mode, or we can think it in terms of real and imaginary part. However you think of it, there are two zero modes. Same calculation for B, because in flat space, the equation for B is the same as the equation for C. Same answer. Okay, so working in terms of holomorphic quantities, we have one CKV, one conformal Killing vector, and one modulus. When I say one, I mean one analytic and one anti-analytic, right? Because it's a complex number. Is this clear? Okay, excellent. Now let us understand.
These equations will always be those equations, but the solution set which have to respect torus are those constants.
The constants.
But if it were not torus, then the solutions would change again.
Yeah, like for instance, if you remember earlier in the class, we worked it out for the sphere. We just took the most general Taylor series expansion. Taylor series around 0 because it had to be analytic, and then we did the math. We went to the infinity patch and asked that it was analytic there also, and then we got 3 conformal Killing vectors and no moduli fields. Okay, but here it's another problem because it's a torus. It's not. Okay. By the way, if you do the calculation in any higher any higher genus, you find no conformal Killing vectors, but moduli fields according to that Riemann-Roch theorem. Okay, so the number of moduli fields keeps growing with genus. Okay. So now let's see, for the torus, let's see if we can interpret these moduli fields. So what are the moduli fields? The moduli fields are changes in the metric of the torus that cannot be compensated for by a diffeomorphism and a Weyl transformation. Okay. So these are precisely, okay, and we're going to go to a description which will make this very clear in a moment. But basically these are, the moduli of the torus are precisely changes in, somebody?
No, the period.
Changes in?
The side. Tau.
Tau.
Yeah,
Tau is the modulus of the torus.
Yeah.
Okay, for instance, you know, let's see how we can make this. Let's see how we can make this. I would prove this for you in a moment. Okay. It may be plausible because we've got this one parameter set of tori, and I will prove you cannot go from one value of tau to another value of tau by Weyl transformations and diffeomorphism. So equivalently, there is no holomorphic map. So you remember the issue of Weyl transformations and diffeomorphisms is whether you could go from one to the other by conformal transformations. Okay, and I think it's sort of clear that any conformal transformation you do, suppose you want to keep this form of the metric, you want to keep it flat. So the conformal transformation would have to be of the form a tau plus b plus c tau plus d. Okay, and it will be clear. Okay, I'll just prove it for you that you cannot go from one value of tau to the other by a diffeomorphism plus Weyl transformation. We'll check this in just 2 minutes.
In other words, the ratio of the two cycles is something physical and
exactly
cannot be changed.
Exactly, and exactly right.
And there's one more parameter. I mean, it's a 2-parameter. Tau is a complex.
Complex. Yeah. So when I say one, I mean holomorphic.
The length is different. Yeah. And the angle.
No, but he was saying there was right.
Yeah,
Right.
Yeah, I mean,
Right. This as a complex number.
yes.
This as a complex number cannot be changed. You know, that kind of the integral over that vector field. We'll check this very carefully because we're going to have to do it anyway to do a calculation. Okay, it's basically the same as this calculation. Because if you could, then this would be 0. Right? Because this thing here was the change in the metric by the generated, you know, this was the part, if you remember the logic of this formula. This was precisely picking out that part that you could not reach by diffeomorphisms and conformal transformations. So equivalently, just calculating this and seeing that it's non-zero tells you that we've got the modulus field. Okay, so changing tau is changing the modulus field. Okay, What are the conformal killing vectors? They're totally obvious. We've already seen them. They're constants. Just translations along any direction on the torus. Constant translations. Okay, a constant translation respects every periodicity. You can think of it as a translation in x and y, or translation in this direction and this direction, or whatever you want. Just these arbitrarily constant vectors, which you can think of as holomorphic and anti-holomorphic if you want. Okay, so these are the conformal killing vectors and the moduli. Now what we want to do is to take this formula and make it operational. Okay. Now, when we worked with this metric here, the way we thought was this: there was a fixed coordinate chart, and we're changing the metric on that space. That's what we meant by g of tau.
Yes.
The way I've presented this metric here for you,
Yeah, it's a fixed metric.
Is a fixed metric but a varying coordinate chart. Okay? In order to use this formula as presented, I don't know if you remember, we had a more sophisticated formula involving Beltrami differentials, which was more suited to this way of thinking. Okay, but let's not get into that sophistication. Okay, in order to use this formula, what I need to do is to transform from this picture to the picture where we have a fixed coordinate chart and a varying metric. Okay, so let's do that. So what I want to do is to find a linear coordinate change. So okay, so suppose what I have is a torus like this, okay, identified with tau. So I've got dz bar identification with tau, and I want to compare that with dz bar identification with tau plus delta tau. I want to compare these two metrics. So I'm going to put them in the same coordinate patch. So what I'm going to do is to take this metric and do a coordinate change on it, which refers it back to the old coordinate system. Okay, so here what I have is z is equal to z plus 2 pi I, and z is equal to z plus 2 pi tau plus delta tau.
That was 2 pi, right? On the real axis.
Thank you. Okay, now what I want to do is to find a coordinate change. Let's call this coordinate change to w. Okay, so let's use Pulczynski's notation for it. So let's say I have z is equal to w plus, now it's going to be a constant metric.
Yeah.
Okay, so it will be a delta tau plus a bar delta, well, a delta tau plus a tilde delta tau bar. Some linear combination of delta tau and delta tau bar, these two complex vectors. And I'm going to take this and plug it back, and I'm going to take this and determine a and b, a and a tilde, so that the periodicities of w. So let me do w is equal to z plus this. Okay, so that the periodicities of w are not tau plus delta tau, but tau. Okay, so let's do that calculation here. Okay, so we know that z is the same point z bar is the same point as z plus 2 pi z bar plus 2 pi, and is also the 2 pi, yeah, 2 pi, and is also the same point as z plus 2 pi tau and z bar plus 2 pi tau bar.
Actually, any combination of the left and right, I mean, z plus 2 pi and z bar plus 2 pi tau bar, I mean, that would be.
Exactly, we could take a times this plus b, m times this plus b,
Exactly.
n times that. But ensuring this is enough, so we won't worry about that. Okay, this we know. So now let's see what the periodicities of W are. Okay, now I'm sorry. Let me choose this to be plus a z plus b z bar. A and B are going to be small. Right, that's what we will need, because otherwise it won't do anything.
Z is tau plus delta tau, and we want W which has tau.
What? We want tau, exactly. Z is tau plus delta tau, and we want W that has tau. So thank you. So plus delta tau plus delta tau bar. Okay, but now we take this W, and on this Z, what do we get? So now, what is W bar when we make the first change? This changed by 2 pi. Okay, this changed by 2 pi, and this also changed by 2 pi. Okay, so we have
The first one will be
W plus A plus B.
unless a plus b is empty.
Yeah, W plus A plus B plus 2 pi.
A plus b into 2 pi.
Thank you, into 2 pi. A plus B into 2 pi plus 2 pi.
Yeah, a plus b plus 4.
Comma W bar. Now, of course, W bar is the complex conjugate of this. And so it will be A bar plus B bar.
Yeah.
Bar plus A bar plus B bar 2 pi plus 2 pi. Okay, what does this tell us? This tells us that this A plus B has to be equal to 0, because we don't want the periodicity of W in this direction to change. Okay, now we also know that this is Z plus 2 pi tau plus delta tau. Okay, now in addition we have what? We have A into 2 pi tau plus B into 2 pi tau bar. We won't keep the tau plus delta tau there, because A and B are themselves going to be small. So second order we ignore. Okay, so plus A into 2 pi into 2 pi tau plus B into 2 pi tau bar. And then the Z bar will be the complex conjugate of this. Right, because we'll just calculate it by complex conjugation. So what we see is that as a complex vector, it must be that A plus B. Sorry, thank you. This is W. Yes, thank you. Plus 2 pi W, and all of this has
That W will not be.
this is not there. Thank you, thank you, thank you, thank you.
We want only the first term.
We want only the first term. So we need that A plus B plus delta tau is equal to 0.
A tau plus B tau bar. B
Thank you, thank you, thank you, thank you. A tau plus B tau bar plus delta tau is equal to 0. Okay, so we have to solve this equation together with a plus b is equal to 0. But since a plus b is equal to 0, a is equal to minus b. So we already knew that this was a into z minus z bar. Okay, so let's write that here. So this was a into tau minus tau bar. Okay, and therefore a is equal to delta tau divided by tau minus tau bar. Is this clear?
With an overall minus.
With an overall minus. Okay, and so we conclude that the coordinate change w is equal to z plus delta tau over minus delta tau over tau minus tau bar. Times z minus z bar does the job. And the key point here is that it's not holomorphic. Okay, that's the key point, that this thing is not holomorphic. Okay, so now this bracket that we have to calculate. Okay, so now we're working in the w coordinate, and let's compute the change in the metric. All we have to do is to take we had the metric was dz bar. Just substitute z in terms of w. Okay, so maybe now that we've got this, we can write z will be equal to w plus delta tau, tau minus tau bar, w minus w bar, and the complex conjugate of that.
To this order.
To this linear order. Right. And therefore dz bar is of course dw bar plus dz into dw into now the complex conjugate of this.
There will be now diagonal terms generated.
Right. dw bar minus dw into delta tau bar by tau bar minus tau plus the other one,
Yeah,
plus dw bar into tau minus tau bar into dw minus dw bar. Okay? Delta tau. Thank you. Now, anything that is dw bar can be removed by a scaling. That was the trivial kind of thing. That will not show up in our calculation. Okay? What will show up is the term that are dw squared and dw bar squared. Those are going to be the key terms. Let's focus on them. What we're going to do is minus dw squared and minus dw bar squared into no, it won't factorize like that. Yes, dw squared into delta tau bar minus, this is correct, minus dw squared into delta tau bar, and then minus dw bar squared into delta tau plus because of this, right? And then 1 over tau bar minus tau.
That does not seem to be correct because below you have an imaginary and above we have got a completely real piece. So that's a
relative minus sign.
Yeah. Sorry. Yeah. The minus will be there.
Right. Okay, and then there's the other piece, which is the d tau bar, but that will not contribute, as we'll see. Okay, so this is the important change. Now, what was the term that we wanted? We wanted del tau, let's say, g times b. We wanted this quantity. Okay? Now, this is the same as what? So let's take del tau of g. Okay? This we're going to get from here. The reason, by the way, that this will not contribute is any contribution that is proportional to g itself, to the diagonal g, will give 0 because b is traceless. It will contract with the trace of b. But this dw square will not give 0 because I'll give.
So that's why you are saying dw
bar is not important, right? But the dw square will be non-trivial because it will contract with b, and the dw bar squared will be non-trivial because it will contract with b bar. Okay, so let's look at the term that is del tau g that came from here. Okay, and that has yeah, that has a
1 over tau bar minus tau. I mean, from that component.
Exactly. It's a g z bar or w bar.
Yeah.
And 1 over, so 2i minus 2i im tau.
I think the GW at W bar is that, because I mean that's 1. I mean GW at W bar is minus 1.
No. This GW bar W bar now will tell us that this contracts with BW bar W bar. Okay, so this will give us BW bar W, but that is BWW downstairs. And then integrated over the whole torus. Is this clear? So the effective insertion factor for this guy is a factor of integral BWW by 2i im tau dw square, and similarly, of course, there will be a factor of BW bar W bar, plus minus, I'm not sure, but it won't matter, im tau bar d2w im tau d2w for the other guy. That's with the derivative with respect to tau bar. Okay, now what is this? This looks like a complicated object, but remember the property that in these insertions, the only part that contributes is when you substitute in the 0 mode. Right? And remember that the 0 mode is constant. We computed, right? It was the solution to the equation del z of b is equal to 0. Okay? And therefore, what we could do is to take this thing, insert it, instead of taking the integral, insert it anywhere, pull that insertion out, and just do the integral. Because we are only getting the 0 mode contribution. You can substitute in the 0 mode, and then take it out again. Doesn't matter. So this gives us this integral is basically a factor of the volume of the torus. And the volume of the torus, anyone who studied parallelograms knows, is proportional to im tau. So this, when you do it up to some numbers, the tau dependence is what's important, and the im tau cancels. Okay? So the effective insertion is a factor of BWW at 0 and BW bar W bar at 0. 0 could be anywhere, because we're only going to get the contribution from the 0 mode, so it doesn't matter where you insert it. Where the im tau dependence is cancelled. Is this clear? Now, in general, we also have to deal with the C0 mode insertions. Now, remember that there's exactly one C and one C bar that is fixed. And the relevant vertex operator is fixed. But, once again, we can undo the fixing. We can undo the fixing as follows. Remember, it didn't matter where we fixed the vertex operator. Okay? So we've got some insertion, let's say at C of Z1, V of Z1. Okay? So therefore, we can replace this by this over the whole torus, d2z, divided by integral over the whole torus, d2z. Doesn't matter at all. Now, this C looks like it's being integrated over, but only the zero mode contributes. Since that's constant, effectively, we can pull, you can replace this by any number, because only the zero mode contributes. Zero mode is the same no matter where the number is. You're understanding, right? So this we can just pull out of the integral. That's some C0. So what we get is integral V d2z divided by integral d2z. But integral V d2z is an integrated vertex operator. Okay? And what we've got effectively is a factor of the volume of the torus. So what is the net result? The net result is we've got a factor of for the net rule is that when we compute torus vacuum amplitudes, it's like we put a B0, a B bar 0, a C0, a C bar 0, and then you divide by im tau the whole thing square. 2 tau. You divide by im tau the whole thing. Wait, it is one factor of this one. Is it one or two factors? Just probably one factor. Yeah, sorry, one factor. I don't. The whole thing square. This. Yeah. So really, we want to just each vertex operator came with a factor of C bar. So what we really had is C bar of Z bar. This was what we had in the rule. C bar. Then we do this once, d2z. Divide by im tau. d2z. Pull out C bar. This becomes the integrated vertex operator, and then we get one factor of the volume of the torus. That is im tau. Okay. So what is the final final result? The final result is that we have this factor, and then every vertex operator can be treated as integrated. Okay? Now, this is a very nice symmetric formula, because it doesn't single out particular vertex operators as being fixed, other vertex operators as being integrated. It has the insertions just at some point. You could choose that point to be wherever you wanted, because only zero mode contributes, who cares? Okay? And this nice symmetric formula applies no matter how many vertex operators insertions we have. In particular, it's a formula we will also use in order to compute the answer with no vertex operator insertions. Okay. The formula as originally written looked a bit ambiguous with no vertex operator insertions, because where are the fixed vertex operators? But you see, the reason that this was okay was the following. The fixing of the vertex operators was needed because there was some diffeomorphism that our original procedure did not fix. Now that diffeomorphism is a dangerous thing when the volume of that diffeomorphism is infinite, because that then gives you infinity or maybe 0 because you're dividing by that diffeomorphism. However, on the torus you see that the unfixed diffeomorphisms were translations along the torus. So what was the volume of that unfixed diffeomorphism? Volume of the torus. So that was not some dangerous thing. We didn't, whenever you've got some infinite, firstly, of course, if you've got some gauge invariance where you've got some field degrees of freedom, you have to fix it, because any field degree of freedom is infinite. We were not in that situation. Our number of unfixed degrees of freedom were finite number. That's still dangerous if the range of integration of that finite number is non-compact. Then that integral could give you 0 or infinity, you have to fix it. But if it is just a finite number, whether you want to fix it or not is up to you. Okay? So in the particular case of the torus, we could have got away if we thought through our original derivation without fixing that unfixed diffeomorphism. And if you work it out carefully, you will just land up with this answer without any of these. We worked out the answer with all the vertex operators in some nice symmetric way, in such a way that it continues, the formula continues to be correct even when there are no insertions. But because the original diffeomorphism that was unfixed was not infinite in volume, we could have just gone through that original derivation and just come back and looked at it carefully, seen you would have got this answer. Okay? I'm not going to work that out for you, but it's plausible that it's the case. Okay? So this is the general formula for the torus vacuum amplitude. We have to do the integral over tau with this measure. You see, this is the whole point of all our rules. When I say abstractly do the integral over tau, it means nothing. But when I tell you exactly with what measure, then it's a meaningful quantity. And this was the point of these ghost vertex operator insertions. They told you exactly what the measure of for the torus integral was. Okay? And we've got the exact insertion factors, and then all vertex operators integrate. So if you want to compute a one-loop amplitude in the bosonic string, you're in business. Not that you would want to compute a one-loop amplitude in the bosonic string since you get infinity because of the tachyon. But anyway, we'll look at how this is modified also for the superstring. Let's first work out the bosonic string. Okay? Great. Any questions or comments about this?
Here there won't be infinities because the space is compact. But sphere we had to put.
A sphere we had to put. And therefore, the question of what is the no vertex of, you said we had to put at least 3. So to have 0, 1 or 2 insertions was ill-defined. Now let's interpret this. You see, the 0 insertions would be the classical to see what 0 insertions means. Let's see what it means for the torus. What is 0 insertions? Well, what you're doing is just the diagram of string theory, torus amplitudes, without any insertions. What is the field theory limit of that?
Just one vacuum loop diagram.
Vacuum loop diagram summed over all the particles in the theory. What does this give you in field theory? It computes the free energy, but in particular, that free energy is just the vacuum energy. It computes a partition function, which is just the vacuum energy, trace e to the power minus, the usual story. Okay? So, this quantity here is like the one loop contribution to the vacuum energy. Okay? The sphere partition function, like this, would presumably be interpreted as the classical part of the vacuum energy. Now, it contributes, it's a diagram which is like nothing.
Yeah.
I think this might I mean, if you think of it this way, but the sphere amplitude, if you stretch it out, is the vertex for
Yeah, I mean, it's
n
one
particles.
vertex integrated over all space. So to speak. I mean, it's some whole space-time integral.
It's like the constant part of the Lagrangian.
Yes, exactly.
It's like the constant part of the Lagrangian. I suppose it's really the constant part of the Lagrangian, not even coupling to the graviton.
Right.
Yeah, so I think it would just be nothing, as you say. You see, the part that
The
couples
volume
to
of space-time.
well, actually, not even that.
No, I mean the total Lagrange. I mean, if we integrate the action, that will be. The
Yeah, but
volume. I mean,
if it's not even the
okay. Then the root g has.
then there would be a root g. Or maybe in some sense what it would be is if you took the square root g
Yeah.
and you expanded it in eta plus h.
Yeah.
Then maybe, yeah, I think that's probably the right way to say it. Suppose you take, the cosmological constant term. Okay, you take that and expand it in eta plus h. Okay, that part is ill-defined. And now, similarly, one-point functions are by themselves not well defined.
One function, there has to be some external.
See, anyway, all one-point functions will evaluate to 0.
Yeah, there has to be one vertex operator inside.
One vertex operator and one vertex operator correlation functions
Yes.
on the sphere
Yeah.
in any conformal field theory, unless that one vertex operator is the identity. For any of the non-trivial operators, let's say for the graviton, the stress tensor will be 0. Even the two-point function thing is not well defined. So, firstly, why was this? It's interesting that we cannot calculate this classical part.
If we ignore the recent claim.
Yeah. If we ignore Maldacena company, and the two-point function once again should not be calculable. At least again, ignoring the recent claim, because we're computing this two-point function on shell, and on shell, what we should be getting is the propagator, or maybe the strip propagator. Okay, but on shell that's either 0 or infinity, depending on how you calculate it. Okay, so all the things that we cannot compute except the 0-point function, which is a bit unsatisfying that you cannot compute. The things that you cannot compute on the sphere are things that are not particularly well defined. The 0-point function is a bit unsatisfying. Let me think about that. On the other hand, this 0-point function in the case of the torus is extremely well defined. It's just the change in the vacuum energy due to vacuum bubbles, and as we will see as we go along, this 0-point amplitude is very physical, because if it is non-zero, then if you take a little small graviton here, at very low energy graviton, this will generate a tadpole for the graviton. Okay, what am I saying? Vacuum energies are generally treated as unphysical in field theory, but vacuum energies are not unphysical in gravity, precisely for the reason we talked about here. Like the vacuum energy is square root g times something. If you take the eta part, you may think that's unphysical, but it's the same number that also determines the coupling to h. Okay, so if there's that term, h couples to it, and we know what that does, right? That's a cosmological constant that will curve space-time. Okay, so this is, even though you might think of this as essentially unphysical, a small modification of this. When we add a 1-point, a vertex operator for the graviton, we'll make it completely physical. It will be a measure of the cosmological constant, in other words, at low energies. Okay, so surely we should be able to compute this. Okay, good. So let's go ahead and actually just compute it. Okay, what we're going to do is to go ahead and compute this for the bosonic string, and then we will repeat the calculation. We'll go through the whole the bosonic string, all kinds of diagrams. We'll do the same for the superstring, and the point is we want to learn. The point is to try to learn some physics from this.
So we'll just pretend that there's no tachyon when we compute this.
Yeah, we will compute it and then throw away the contribution of the tachyon, as you say. I mean, we get a divergence, but we'll be able to isolate out that divergence.
It can be regulated.
Hey, oh yeah, you'll see. Okay, so how do we do the computation? Okay, that's pretty easy. We use an ingredient that we've already computed at some point, but we'll quickly do it again. So, what do we have to do? We have to take the partition function of our theory. So what we have to do is to compute the torus partition function. But what is the torus partition function? It's trace e to the power minus beta h. Or more precisely, it is q to the power L0, q bar to the power L0 bar, where q was equal to e to the power 2 pi I tau, and q bar was equal to e to the power minus 2 pi I tau bar. Okay, so what we're supposed to do is to compute trace of q 2 pi I tau, q bar to the power minus 2 pi I tau bar times, now we mustn't forget that these are there, so we'll put those in.
This is q to the L.
Ah, thank you. Thank you. Q to the power L0, q to the power L0 bar, B0, C0, B0 bar, C0 bar. And then the next thing we have to ask ourselves is, are we actually computing the trace? What we're doing is computing the partition function with the boundary conditions for B and C fixed by the boundary conditions of diffeomorphisms. In particular, the boundary conditions for B and C are periodic as we go around the circle. But B and C were anti-commuting fields. If we were actually computing the trace, they would be anti-periodic as you went around, let's say, the time circle. However, they are periodic. Okay, so what we are actually computing is this times minus 1 to the power n. So the Hamiltonian interpretation of the thing that we have to compute is this, and then we are supposed to take this and integrate it d2 tau over m tau. This is the quantity we actually want to compute. This, the path integral that we have to do in Hamiltonian language, is this object. Is this clear? Okay, we have to do this over the X CFT and the BC CFT and put the results together. I mean, we have to take the trace over the combined CFT, and then we get what we get. Then do the integral over tau. Okay, so let us quickly do the calculation. Let's first do it for the BC CFT. Let us remember what the spectrum of the BC CFT was. Okay? Now, L0 and L0 bar are the oscillator Hamiltonians plus the contribution from the zero mode energy. Now, since the net zero mode energy of the whole theory is proportional to the net central charge of the whole theory, the total zero mode energy is going to cancel out. Right. Take any one X CFT. It has a zero mode energy. Okay. Now, that zero mode energy will be multiplied by 26. It will be overall outside and be multiplied by 26 because there are 26 X's. However, that zero mode energy is exactly minus of the zero mode energy of the BC system, because the zero mode energy is determined by the central charge, And the BC system precisely has minus C equals minus 26,
Yeah.
whereas the XCFTs have C equals 26.
Yes.
So if we just ignore the zero mode energies everywhere consistently, we'll land on our feet.
Yes.
No, we're doing the wrong thing CFT by CFT, but when we put it all together, we're landing on our feet. Okay? So what I'm going to do is to ignore the zero mode energies and proceed with the calculation. Okay. Right. Okay. So fine. Maybe we do the x's first. Any given x, what were the oscillators? The energies of the oscillator started. There's the zero mode of the oscillator, which we have to take in account separately. And then there are the actual oscillators. The actual oscillators have energies 1, 2, 3, 4. Okay? So clearly that is going to be product over n, 1 over 1 minus q to the power n, 1 over 1 minus q bar to the power n, to the power 26. This is the oscillator part of the XCFT. Now what about the zero mode part? I don't mean the 0 point energy. I mean the zero mode part of the XCFT. This, remember how we compute. The string world sheet action was 1 over 4 pi alpha prime and then del x the whole thing squared. We put in in order to get the contribution just from the zero modes, we do the integral over sigma. So 1 over 2 alpha prime integral x dot squared. Then we remember that this is exactly the Hamiltonian of a non-relativistic particle, the Lagrangian of a non-relativistic particle of mass m is equal to 1 by alpha prime. So the spectrum of this zero mode part is the spectrum of a non-relativistic particle of mass 1 over alpha prime. So it is, the Hamiltonian of that is p squared by 2m, so alpha prime by 2 p squared. Okay? And therefore the partition function of this is the integral of now this is q bar. This would be L0 plus L. I always get mixed up with the factors of 2. I think it's q bar. It's q. In this case, L0 is equal to L0 bar because it's the zero mode. And it's q bar to the power.
Yeah, the energy and the mode. Because
Am I missing a factor of 2? That is the question. Anyway, if I was missing a factor of... I'm not going to keep track of that constant anyway. Okay. At this dp, I should do it more carefully. I should check whether I'm missing a factor of 2 or not. Okay. So this would be
q bar.
u bar. Thank you. So this would be e to the power log of q bar. Maybe I should write this in terms of im tau. Q bar is 2 pi I tau minus tau bar.
Yes.
So 2 pi I, it's minus 2 pi im tau with a factor of 2.
Yeah.
There's some factor of 2. I think actually this will work out. Anyway, we won't keep track of such things so carefully. Okay, so up to factors, it's e to the power minus im tau times alpha prime p squared. And therefore, when you do the integral over p, you get 1 over square root im tau square root alpha prime. And that's it. And then some factors of pi. Okay, so the whole thing here is this times 1 over square root of im tau, I'm only keeping the tau dependencies, okay. Im tau to the power 26. And then if we wanted to, okay, let's do it because this is how books normally do it. If we wanted to, we would also keep the the zero mode contribution here and also let it cancel with the ghosts. If we wanted to do that, the zero mode contribution would be q to the power minus 1 by 24, right? Because the vacuum energy was 1 by 12. That corresponded to q to the power minus 1 by 24. So it would be q to the power minus 1 by 24. Let me check the minus sign is correct. If tau was imaginary, it would be it should have been e to the power minus 2 pi times L0. And L0 is L0 is negative. Im tau. And so, yeah, and so we should have got e to the power plus im tau. So q to the power minus 1 by 12 for q bar to the power minus 1 by 24. This is I times, I think that's right. We're getting this thing is e to the power positive number times im tau, right? Because this is q e to the power 2 pi I tau minus tau bar. This is into minus 1 by 24. Now tau minus tau bar is I times im tau. So minus into minus is I, and then there's additional minus, it's plus. Okay, good. So, this is for each, but there are 26 of them, so it's 26. So that's q bar to the power 26 by 24 with a minus sign. This is the full partition function finally for the matter CFT. Is this clear? Okay, let me just check. Where is his answer? Okay, Q, right, perfect, 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 perfect. Yeah, this is correct. Okay, excellent. So this was the partition function for the matter CFT. Now we want to do the same calculation. Now we want to do the same calculation for the Ghost Cft. Okay. Now with the Ghost Cft, at first you might think, something strange is happening. Okay. At first you might think something strange is happening. And you might think that because, look, we're computing trace minus 1 to the power f. But as you know, the Ghost, the BC has 0 modes. There's B0 and C0. And if you compute psi and the contribution of the psi and C0 psi to this trace are equal but opposite because of the minus 1 to the power f, and will cancel. So for every state, there is another state which you can get by acting on that state, by acting. So let's say that we start with a state that is annihilated by B0. Act on that state with C0, that's another state with the same energy. So it doesn't change this L0 and L0 bar. It contributes the same way in Q, but because of the minus 1 to the power f, you get an extra minus sign, so you might think you get 0. And indeed, had these insertions not been there, this quantity would have been 0. In terms of path integrals, we would have got 0 precisely because of the thing that we keep saying in string theory. We're doing a path integral with fermionic 0 modes, and there's nothing to absorb it. That's the Hamiltonian version of the statement. Well, in path integrals, having these insertions saved us. It also saves us from the Hamiltonian point of view. Because you see, because of the 0 modes, we can actually, as we've said many times, replace these insertions by insertions of just the 0 modes. Okay, so up to some sign, this is C0, C0 bar, B0, B0 bar. Maybe I'll put it the other order. No, I'll put it this way. Okay, so now we've got this object here. So now imagine you've got a trace. So it's got like some M, then there's some C0, C0 bar, B0, B0 bar. And then you're supposed to compute M. You're supposed to sum over all states. But this quantity here, if this M state is a state which is C0 on something, this quantity will give you 0. Because C0 squared 0. So you see, you only get contributions from states that are annihilated by C0 or by B0, depending on which way we put it. So of the doublet of states, it picks out exactly one. Okay, and then you repeat it on that side. Okay, so the role of these insertions is the following. Every state comes in a doublet in the holomorphic side and a doublet on the anti-holomorphic side. And these insertions, instead of, if we were to sum over the contributions of all states in this doublet or in this doublet, we would get 0. Because they contribute oppositely because of the minus 1 to the power f. These insertions exactly allow you to get contributions from one state among those 4. That is their whole role. Once we've understood their role, we erase them. Okay? So we don't look at multiplets under C0 and B0. Take one state in those. And now we have minus 1 to the power f. Now we're in complete business. Is it clear? Okay? Now it's very easy to do the calculation because now we're not supposed to take into account the 0 modes. That was the confusing thing. Okay, so now what we get? Well, firstly, these guys are fermions. So instead of getting 1 over 1 minus q in the denominator, we would think we would get 1 over 1, we would get 1 plus q in the numerator. But we don't get 1 plus q, we get 1 minus q. Why? Minus 1 to the, because every time you add a fermion, you get an extra minus sign. So what do we get? We get product m is equal to 1 to n and 1 to infinity, 1 minus q to the power n. But there's one such thing for the c's and one for the b's. So whole thing squared, 1 minus 1 q bar power n, the whole thing squared. Holomorphic, anti-holomorphic. Clear? And then there's the 0 mode contribution. That will be q bar to the power now plus 26 by 24. right? Because it's the central charge for these things, instead of being positive, is negative. The 0 mode contribution was q to the power c by 24, and c is minus 26. I mean, q to the power minus c by 24, and c is minus 26. Okay, so this here is the partition function for the C ghosts. Now notice this. Notice that what we get here exactly cancels the oscillator contributions of 2 of the x's. Moreover, what we get here cancels that exactly. That 0 mode part exactly.
And what remains is 24.
Right, exactly. So what remains is d2 tau divided by d2 tau divided by im tau. That was from the original torus formula. Then we have 1 over im tau to the power 26. 13. And im tau to the power 13. Then we have product n is equal to 1 to infinity 1 over 1 minus q to the power n 1 over 1 minus q bar to the power n to the power 24. Okay, and that is, yeah, that is all. That is all. But before declaring victory on this, so this is our final answer. But before declaring victory on this answer, is it? Yeah. Okay. We take 5 minutes. Yeah. Before declaring victory on this answer, we'd like to see. We'd like to see that this answer is modular invariant. Okay. We've computed a partition function in a torus. Now that partition function in a torus should be a geometrical object. For instance, if we do tau goes to 1 by tau, or tau, any SL2Z transformation shouldn't change the answer. Now, look, this quantity here was a CFT partition function and was modular invariant. Okay? In fact, the quantity be this quantity q to the power 1 by 24 1 minus q to the power n is sometimes called eta of q. Okay, and it is our famous result that eta of minus 1 by tau is equal to eta of tau times minus I tau to the power half times.
No half equal, right?
Square it. Thank you. Okay. And now we need also to understand how tau2 transforms under modular transformations. So Im tau, exactly. So suppose we do, suppose tau is equal to tau 1 plus I tau 2. And we do this transformation. Okay. So we take minus 1 by tau 1 plus I tau 2. So this we can write as tau 1 minus I tau 2 over
tau squared with a minus.
Tau 1 squared plus tau 2 squared.
Yeah.
With a minus, as you said. Minus. And we see that this is, so tau 2 prime is equal to tau 2 over tau bar. Okay. So because of this, the object im tau times eta of tau, this quantity is modular invariant.
So, is there any issue about which branch to take in that square root?
Which branch to take in that square root? Now this, of course, this formula here must be correct with a particular branch. I think that it is the positive one when tau is positive imaginary. So when we're here,
Yeah.
now this is like where the partition function is positive temperature. This should be, in this region, the square root is positive. Okay, that defines. Yeah. Right, yeah, it's true only with a particular choice of branch, but I think it's this one. Okay, and can you see that this quantity now tells you that so what we want to do is to check that im tau prime times eta of minus 1 by tau, where tau prime is minus 1 by tau, so im of minus 1 by tau, this is equal to im tau times z of tau, eta of tau. But we know that im minus 1 of tau is eta of tau times square root of minus I tau, and that's square root of tau 2. That's, yeah, square root of tau 2. Right? Because square root of minus I im tau.
Well, there's a minus I in tau there?
What? Yeah, there was minus I.
Oh, I thought it was
No, minus I tau. Sorry. Minus I. Sorry. Minus I tau. Yeah, just let's keep it. Sorry. Just keep it here. Yeah. Very good. But what do we know? We know that im tau, we want im this, so let's write this out. Let's write out the LHS. So the LHS tells us is tau 2 divided by tau bar the LHS, I think that the right thing is this times eta bar. That this will be the modular invariant, I think. Okay, let's check. Eta bar minus 1 by tau. Yeah, z bar, eta bar of tau bar. Because this is actually what we want, right? There's an im tau for a double factor. Yeah. So let's see. So there's tau 2 divided by tau bar. Then we get square root of some sign tau bar. Okay. Times eta tau bar. This is equal to tau 2 I wanted square root, right? I'm sorry it's to be so.
Do you want it to be cancelled?
I think
I want it to be cancelled and I want square root here, right?
Yes.
Thank you.
Yeah.
Yeah. Thank you.
Square root in tau.
Square root, and then that'll be eta tau bar. Now it works. This cancels this. Square root tau 2 is square root tau 2. So sorry, after all these iterations, this quantity here is nice and modular invariant. Okay, therefore this partition function here by itself was nice and modular invariant. It was 1 over im tau eta of tau eta bar of tau bar to the power 26 square root. Okay, so that quantity was by itself a nice modular invariant object.
The measure is modular invariant.
Wait, we have to go in steps.
Okay.
Okay, now the quantity, the other quantity. What about the BCCFT? Now the BCCFT was what? Remember, what we got was eta of tau bar, the whole thing squared, but those etas ate up only 2 powers of this QQ bar out of the 26 by 24.
Yeah.
So what was left over was QQ bar. Because remember, it came with QQ bar to the power plus 26 by 24. The 2 over 24 was eaten up by in going to the etas. Okay? And then, so this is what we have. Okay? So this quantity, okay, this quantity is nice and modular invariant, but what's left over is this QQ bar. What?
Square root in tau, which is needed. If
No, but
modular in
QQ bar is not im tau, right?
No, but I mean, what I'm saying is that.
Yes. Yeah. Sorry, you're right. Let's write it in terms of im tau. So there's im tau square root squared. So then we would have to multiply by im tau. Okay. So now we have to deal with this and that factor there and get modular invariance. Since QQ bar I feel I've messed up on. What have I messed up on? Okay, anyway, let's not miss Rajdeep's talk. So let's continue this next time. This im tau square is what we need, because d2 tau divided by im tau square is the modular invariant measure on the torus. So this extra factor of im tau is great. This QQ bar I've messed up on somehow.